The main subject of this course is linear algebra. And linear algebra originated with the problem of solving systems of linear equations. Consider the following system of equations. So here we have 3 equations with 5 unknowns. And our goal is to describe solutions of this system. So that is the values for our unknowns for which all 3 equations will be satisfied. This is an example of a system of linear equations. So what makes these equations linear? So here, each equation is a sum of variables with constant coefficients. And so here we don't have any squares or cubes or trigonometric functions involved. Our goal is to develop general methods of solving systems of linear equations like this one. And we want to make our method suitable for the use with computers. Now, how can we write this system of linear equations in a more efficient way? So we point out here that the names of the unknowns are rather not relevant. So we can replace the names of variables with different notations. What is important is the coefficients that are in front of these variables, and also the coefficients that appear in the right-hand sides of these equations. So an economical way to encode this system of equations is to drop the names of the variables and to write down only the coefficients in front of them. So this leads to the concept of a matrix of a system of linear equations. So let's write down the matrix of this system. So I'm going to write down just the sequence of numbers that are coefficients in front of these variables. And the first coefficient, which is not written here, but it's really the coefficient of 1. The second variable has a coefficient of 3. Then the next one, it's minus x3, so this is minus 1 times x3. So here we should write minus 1 to account for sign. Then we have 2 and 2. And to indicate that what follows is in the right-hand side, I will put a vertical bar here, and I'll write a 3 here. So then we take the second equation. So the coefficients are 2, 6, minus 3. And then we have to be careful. So we see that the next term is x5. And there is no x4 term. So this means that in this position, we should record a 0 to indicate that the x4 term is missing. And then the coefficient at x5 term is 1. And the right-hand side coefficient is 5. And then the last row will be 3, 9, minus 4, 2, 3, and 8. And so then we enclose this with brackets. And so this becomes the matrix of this system of linear equations. So this matrix has 2 parts. So there is the main part here. So this is called coefficient matrix. And if we include the right-hand side column, then together this will be called augmented matrix. It's important to remember that rows of this matrix correspond to equations. And columns of the coefficient matrix correspond to variables. So, for example, the 4th column corresponds to the variable x4. What is the general idea for solving systems of linear equations. The basic idea is to express one of the variables, say x1, from the first equation. So we can write x1 is equal to 3 minus 3x2 minus x3 minus 2x4 minus 2x5. And then substitute in equations 2 and equation 3. And if we do this, we will eliminate the variable x1 from the last two equations, and we'll get some simpler system of linear equations. We can make this method more efficient. There is no need to express one of the variables here. Instead, we can operate with equations themselves. So what we can do here is we can add to equation 2 a multiple of equation 1, or rather, we will take equation 2 and subtract 2 times equation 1. So if we do this, so what will happen? So we have equation 2, which is 2x1 plus 6x2 minus 3x3 plus x5 is equal to 5. And we subtract 2 times equation 1, which is x1 plus 3x2 minus x3 plus 2x4 plus 2x5 equals 3. So what will be the result of these operations? As a result, so here we get 2x1 minus 2x1. That will become 0. So here 6x2 minus 6x2 will also become 0. Here we have negative 3x3 minus negative 2x3. So this will become minus x3. So there is no x4 here, and we subtract 4 times x4. So we get minus 4x4. And we get x5 minus 4x5. So minus 3x5. And the right-hand side becomes 5 minus 6. It's negative 1. So what we see is if we take equation 2 and subtract 2 times equation 1, then the variable x1 is eliminated. And so we're achieving our goal. And we get a new equation that does not involve the variable x1. So this is more effective than expressing x1 and then making a substitution. So likewise, to eliminate x1 from the third equation, so what we should take is we should take equation 3 and subtract 3 times equation 1. And this will become a new equation 3. So here, so with this prime here indicates that this is our new equation. How can we translate these operations with equations into the language of matrices? So remember that equations correspond to the rows of the matrix. So what we do here can be written in the following way, that we take row 2 and subtract 2 times row 1. And this is our new row 2, which we will denote with the prime. And so likewise, to transform equation 3, we will take row 3 and minus 3 times row 1. And this will be our new row 3. So what is the resulting matrix that we get? So the resulting matrix will be like this. So the first row stays the same. So 1, 3, minus 1, 2, 2, 3. And then we take row 2 and subtract 2 times row 1. So we get 0 here, 6 minus 6, that's 0. Minus 3 minus negative 2, that's minus 1. 0 minus 4, that's negative 4. And 1 minus 4, that's negative 3. And 5 minus 6 is negative 1. So we can see that this is exactly the row that corresponds to this equation here. And for the last row, so we take row 3 minus 3 times row 1. So here we get 0. 9 minus 9 is 0. Minus 4 minus negative 3, that's minus 1. Then 2 minus 6, that's negative 4. And 3 minus 6, that's negative 3. And 8 minus 9, that's negative 1. So we get this. We can go back and forth between systems and matrices. So if we have this matrix, then we can easily transcribe this as a system of equations. So we have x1 plus 3x2 minus x3 plus 2x4 plus 2x5 is equal to 3. And then we have negative, so this is the third column. So the third column corresponds to the variable x3. So here we have negative x3 minus 4x4 minus 3x5 is equal to negative 1. And minus x3 minus 4x4 minus 3x5 is equal to negative 1. So we see here that equations 2 and 3 are now the same. And we can easily eliminate the variable x3 from the last equation by taking the difference. So we take equation 3 and subtract equation 2. And so this will be new equation 3. So in the language of matrices, so here we're saying we take row 3 and subtract row 2. And this is our new row 3. So let us write down the resulting system and the matrix. So the corresponding system of equations will be x1 plus 3x2 minus x3 plus 2x4 plus 2x5 is equal to 3, and minus x3 minus 4x4 minus 3x5 is equal to negative 1. And the last equation completely cancelled out here because the difference between these two equations is 0. So for the matrices, so the matrix will be 1, 3, negative 1, 2, 2, 3, 0, 0, negative 1, negative 4, negative 3, negative 1. And the last row is completely a row of zeros. So what we point out here is that 0 rows in the augmented matrix correspond to null equation. So there is empty equation that corresponds to the 0 row. Let us make one more step simplifying this system of equations. So what I want to do is I want to switch sign at the second equation. So what I'm going to write down is, let's take new equation 2 to be -1 times equation 2. So then this gives us the system x1 plus 3x2 minus x3 plus 2x4 plus 2x5 is equal to 3, and x3 plus 4x4 plus 3x5 is equal to 1. For matrices, the corresponding transformation is multiplying row 2 by -1, and here is the resulting matrix. So now we can see that the new system of equations that we've got is considerably simpler than the original system of equations. And we simplified it to the point where we can analyze the solutions of this system. So let us express x3 from the second equation. So we get x3 is equal to 1 minus 4x4 minus 3x5. And let's express x1 from the first equation. So we get x1 is equal to 3 minus 3x2 minus x plus x3 minus 2x4 and minus 2x5. Now, here we can also eliminate x3 from the second equality. This will give us x1 equals 3 minus 3x2 plus, so instead of x3 we write 1 minus 4x4 minus 3x5 and minus 2x4 minus 2x5 equals, so we have 3 plus 1, that's 4, minus 3x2, then we have minus 4x4 and minus 2x4, minus 6x4, and combining the terms with x5, we get minus 5x5. Now, so we note these two expressions. So here we have an expression for x3, and here we have an expression for x1. So we realize that we expressed x1 and x3 in terms of the variable x2, x4, and x5. By assigning arbitrary values to variables x2, x4, and x5, we will recover the values of x1 and x3 that will satisfy the original system of linear equations. So we can record the following description of solutions. Assign arbitrary values to x2, x4, and x5, and recover values of x1 and x3 from the relations we found. In particular, we see that this system has infinitely many solutions. Let us summarize. What kind of transformations do we need for equations so that we can simplify the system of linear equations? So we have 1. Add to an equation a multiple of another equation. Two, we can multiply an equation by a non-zero scalar. Well, scalar is just a number. So when we say multiply, this as a special case also contains the case of division. And 3, sometimes it is convenient to switch the order of equations. Now, when we translate this into the language of rows, then we get something which is called elementary row operations. Now, we have type 1. So we take row number I and make a new row number I by taking all row number I and adding a multiple of row number j, where I is different from j. So type 2. Multiplying a row by a non-zero scalar. So we say row I prime is equal to k times row I, where k here is non-zero. And type 3, so we can swap row I with row j. What is the reason for requiring that this scalar k is non-zero? Well, if we take a row and multiply it by 0, then we wipe out all the coefficients in this row. And if we do this, we will lose information. And we don't want this to happen. And because of that, we require that this coefficient k is not equal to 0. So for a similar reason, we have to issue the following warning. So we apply only one elementary row operation at a time. Let's give an example showing how things can go wrong if we ignore this warning. So imagine the following matrix. So 1, 2, 1, 2. And suppose we try simultaneously do the following two operations. We say row 1 new is row 1 minus row 2, and row 2 new is row 2 minus row 1. So then this will bring this matrix to the matrix where both rows are erased. And so this is obviously wrong. Right? So these two systems will not be equivalent. So the flaw in this transformation came from the fact that we simultaneously applied two elementary row operations. Each of these elementary row operations on its own is a valid one, but applying them together produces an incorrect result. And so because of this, so we have this warning that at one step we're allowed to apply one elementary row operation. So later on we will discover some shortcuts, but to begin with, so let us stick to this rule, one elementary row operation at a time. Let us introduce indexation of entries in a matrix. So for this matrix, we will denote the entries in the following way. So we'll have A11, A12, A13, A14, A15, and the coefficient in the right-hand side we'll call B1. And we have A21, A22, A23, A24, A25, and the coefficient is B2. And the last row will be denoted A31, A32, A33, A34, A35, and the coefficient is B3. Now, we will need this indexation for two reasons. One, to carry out proofs, and two, so this form of writing is convenient for computers. So in particular, to translate this, so here the coefficient, so A32 is the coefficient here. So this is the coefficient in row 3, column 2. And so A32 here is equal to 9. And B3 for this matrix is equal to 8. So in general, we will denote the coefficient matrix as m by n coefficient matrix, and we'll call it A. So here m is the number of rows, and n is the number of columns. And remember that rows correspond to equations, and columns correspond to variables. So when we say what's the size of the coefficient matrix, we specify what's the number of equations and what's the number of unknowns in our system. In particular, here we have a 3 by 5 coefficient matrix. And 3 by 6 augmented matrix. Now, for a general m by n matrix A, we are going to write it in the following way. So we'll have A11, A12, dot, 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 up to A1n. Then entries in the second row are A21, A22, up to A2n. And in the last row, we have AM1, AM2, AMN. given this coefficient matrix, the general system of linear equations that corresponds to this matrix will be written as follows. A11x1 plus A12x2 plus A1n xn is equal to B1, A21x1 plus A22x2 plus A2n xn is equal to B2. And finally, the last equation, number m, will be am1 x1 plus am2 x2 plus amn xn is equal to bm. And this will be how we denote the system of linear equations.